This is Math Analysis, Pre-Calculus, Section 7.5. We're talking about linear programming. This is going to be part 2 of the notes. Here's the example where we left off. And remember that our steps to maximize a function subject to some constraints, we are going to graph them, and each of the inequalities should be greater than or equal to or less than or equal to in our examples. We're going to graph those inequalities, find what's called the feasible region, and then we're going to check each vertex to find the greatest or minimum value. So it's a 3-step process, okay? Now, we said that no matter what, the answer is going to be at a vertex. And we have to talk about why that makes sense. Because in this example, how do we know that x plus 2y, some function x plus 2y equals, well, how do we know that this doesn't give you the maximum answer that goes straight through it? Or this line, or this line. And so what we're going to do is, I'm going to put these functions into Desmos. And I'm going to go ahead and try and graph that. So here is a graph with 3 constraints, and you can see it looks exactly like our picture that we drew. And what happens if I put, say, 0 equals x plus 2y? Okay, so that is our standard graph of the function, that purple line there. And then if I put, notice that that hits the region. That's this one right here. But if I were to put, say, another expression, but let's put 1 equals x plus 2y. But so you see how that function is a little bit larger. Okay, so that black line there is larger, which means 0 is not a maximum. And we can go through this process graphically. We could write some sort of code or program that checks every single x plus 2y line. So let's say if we did 4. Well, that should be a little bit better of an answer, but it's not quite the maximum. And so the why a vertex always gives you the maximum, let's put 1 more, and then let's put 12, because that was our answer here. 12 equals x plus 2y. And notice that it intersects at that top part of the graph right there, that blue line. So you can imagine an infinite number of answers in the feasible region, but there's only one that gives you a maximum. That is our reasoning, or proof, if you will, that we are going to find coordinates at the vertex. Alright, remember, 3-step process, okay? I encourage you to pause the video at this time, see if you can maximize the function f equals negative 3x plus y subject to the constraint y is less than or equal to x minus 2, x is less than or equal to 6, y is greater than or equal to 1. Alright, here we go. Now, got to change one line there. So I have two of them graphed. I have to graph y equals x minus 2. Alright, and then that's going to change some of my vertices here. So let's go through it. My feasible region is going to be y is less than x minus 2, x is less than 6, so it's got to be to the left of that vertical line, and then y is greater than 1. So here's my region. It's that little triangle. And we have 3 vertices. So vertex A looks like it's 3, 1. And if I plug that in, I'm going to get an answer of negative 8. Vertex B looks like it has coordinates of 5. Oh, let's see. Hold on, I got to move this one over. Okay, that's better. Alright, so vertex B is going to be a 6, 4. And then vertex C is going to be 6, 1. Now if I plug in 6 and 4, I'm going to get an answer of negative 14. And if I plug in 6 and 1, I'm going to get an answer of negative 17. Okay, now, which point maximizes the function negative 3x plus y? The answer is not B. You would think that because that's the highest in your picture, that's the maximum, but it is not. The answer is point A, because negative 8 is the highest value. You could go ahead and put that into a graphing calculator or some sort of graphing utility like Desmos and check and see that that's the highest value. So just like linear systems of equations, it is possible to have multiple feasible solutions or no solutions. The feasible region can be unbounded. This means that for an objective function f to have a minimum, but it could be that no maximum exists, and vice versa. Let's do another. Find both the minimum and maximum, if they exist, of the function f of x, y equals x plus 4y, subject to the constraints that y is less than or equal to negative 2x, negative 5 is less than or equal to x plus y, and y is greater than or equal to 3. So let's graph these things. Y equals negative 3. It's going to be right here. X plus y is greater than or equal to negative 5. Okay? And then let's graph y equals negative 2x. Where is our region? It must be greater than the horizontal line to the right of the purple line and below the blue line. So it's going to be this region right here. with vertices here and here. Most of the time you can just look at the graph and say, okay, so our vertex for A should be -2, -3. The vertex for B, that should be, now my graph is off, so what you need to do is take y equals -3 and plug that into y equals -2x and solve the system. So you would actually get 3/2, comma, -3. Okay, next, let's plug those into the function f of x, comma, y equals x plus 4y. For the first one, I'm going to get an answer of -14. And for the second one, I'm going to get an answer of -10.5. Now you need to do a little bit of analysis and say, okay, at point A, it's -14. At point B, it's -10.5. So it's probably likely that the function increases that way. So we have to say that there's a minimum possible at -14. However, no maximum exists. The reason for that is because the function is unbounded at the top. Alright, that is it for today. I am going to ask that you please comment on this video in order to earn credit, and then have a nice day.